Hello, you're welcome to this presentation on risk and capital budgeting. Now, this chapter is almost a continuation on what we have been doing. Just to give you uh, an overview of what we have done in the past and see where the connection comes into play, we did look at valuation and rates of return. We also looked at a chapter on cost of capital, again, which is an instrumental when it comes to capital budgeting. And if you recall, we focused on a weighted average cost of capital. We also covered something on capital budgeting. Uh, And these are basically the methods, capital budgeting methods, the methods we used to assess investment project, where in this case we looked at the uh, internal rate of return, we looked at the net present value, we looked at the modified internal rate of return. We also looked at the payback method, which we said it still does not make no sense, but it's a method that's outside of there. So the payback method, we also did that both using raw cash flow and also using the discounted cash flow. So just keep in mind, again, the goal for us here was if you have to choose between two, three investment projects, which one are you going to use? And these methods just helps us on how we can make those choices. But remember, conversation, when we are looking at all these issues, we were looking at one rate, and we are saying, yes, we discount the cash flows or the inflows and the outflows using a particular discount rate. Again, that discount rate was not changing because you're talking about two project A and a project B, and where again we saw maybe project A has only could be maybe 4 years, and then you have another project which could be again 6 years or 7 years. But in terms of discounting the cash flow, that is determining the net present value, we used just the same number. But again, that we're going to put into question as we try to look at risk and capital budgeting, because what we were doing in the previous chapter, we were assuming that investment A or project A has the same risk as project B, but that's not true. uh, uh, what you end up seeing is where project B maybe has more risk than project A. And given that, then we need to do something when it comes to that discounted. So we're going to discuss that later on in this, in this chapter as we try to look at capital budgeting later on. So I'm going to try to split this into two presentations. So in my first presentation, which I'm going just to call part one. In part one, I'm going to focus on risk. And then I'm also going to look at part two. And the part two, I'm now going to look at the capital budgeting aspect. That is how we then use the risk element and incorporate this into capital budgeting. So that's how I'm going to address those issues. So let's move into the first part and try to understand or try to look at what risk is, and we see what we can learn from this. So we know that again, I'm going to borrow, or we are basically borrowing from mathematics. So those who have taken statistics or any other class, so if you have taken statistics, then you are more familiar with the chart, for example, you're seeing on the board. Again, this is just a probability distribution of some data of various that's different projects, A, B, and C. And because we are trying to, so we use mathematical concepts to try to measure and to try to understand risk. And by definition, risk is basically the variability or the dispersion of certain outcomes, possible outcomes. In other words, the way the outcomes are dispersed is a sign of how much risk is inherent in that particular investment. So if you have three projects here, A, B, and C. Again, if you look at just the data and you see how the data and the format of the distribution here, again, what I'll do is just to give you a sample, if you want to use the normal distribution, what you do in this given example, you could just say, this is what you're seeing. In this one, what you have is basically that. In this one, what you have is basically that. Again, my point, I just want you to see what is happening with these three data sets. I might not have drawn it clearly, but it gives you the point that if somebody was asked also ask you which of these three distributions has the lowest risk, and I'm sure most of you are going to say that project A has the lowest risk. There's a lower risk here. Then, of course, with a project C, because then C tends to have a higher risk than, of course, project A. Why? Is because you're looking at the distribution of the data and you're seeing that in project A, most of the data is closely to the mean. So in other words, they're clustered around the mean, not far away really from the mean. Whereas in investment C, you could see the data is widely spread. So there's a higher dispersion in investment C than investment A. So if that's the data over returns, if you're looking at the data over returns that have been plotted again in probability distributions, what you end up seeing is where the data for C that are widely spread, and because of that, there's a higher risk, and therefore the point is the chance of you gaining or the chance of you losing is more in investment C than it is in investment A, because investment A, the data is closely to the mean. In that case, you have the risk level there is basically going to be low. We're going to see this later on, just how we add the math aspect to risk and so on. So basically, when you're trying to measure risk, again, we use statistical methods and we use the standard deviation, and we also use the coefficient of variation. And I'm going to explain later on why, maybe the coefficient of variation is a better measure than the standard deviation. But just to give you the formula, when you're trying to compute that standard deviation, we know that what you're doing is, first of all, you determine the expected value, and that is the weighted average. So you determine, first of all, the weighted average. And I just call this the mean, simply, just for simple understanding, is the mean, but it's basically the weighted average. So you determine the mean of the data, and then the next thing you do, you take now the deviation from the mean. For every possible outcome that you have, let's say you have an outcome D1. So what you do, you take D1 minus, of course, the expected value, and then you also have maybe another outcome, and what you do, you do the same thing. So all these are basically the deviation, how far the values or the outcomes are deviating from the mean. This is what we refer to as the deviation. But what we end up doing is we square the deviation. And again, remember from your math class, we squared the deviation so that we get what we call the absolute value, right? So that gives us the absolute value. So that in case you had a negative value here, that value becomes positive by squaring that value. So we get the absolute value, and then what you do, you'll multiply each squared deviation. So then you take each squared deviation and you multiply this by its associated probability. So probability 1, that was mean probability 2, and you multiply this by probability 3. It's by its related probability. And then what you do is you're going to sum the values together. So this is the values, and then you sum all those values together. So you have all your deviations, square deviations, and multiply by their probabilities. You sum all the values together and you find the square root. This gives you what do we say, the standard deviation. Again, but standard deviation is a measure of risk. So in other words, the higher this value, of course, the higher the risk. The lower the value, of course, the lower the risk. So the higher the value, the higher the risk. The lower the value, the lower the risk. So we use that concept to understand or to measure risk. So that's how we use this concept. And then the other measure or the other statistical method we use is the coefficient of variation. So the coefficient of variation, what you're doing again is just taking your standard deviation and you divide this with the expected value, that's the mean, and this gives you another measure of risk, a more clear measure of risk. Again, you just look at the formula. So if you just look at the formula, what do you end up getting? In other words, you're saying here this value is giving you the risk per unit of return. So if you just look at the formula, what you're going to get here is sorry, what we're getting here is the risk level, how much risk per unit of return. Again, it's a clear measure, and I'm going to show you why the coefficient of variation becomes a better measure than even the standard deviation, especially if you're comparing, a group of investment projects, 2 or 3 or 4. And again, I'm going to show you how we get to there. So again, just coming back to what we discussed in terms of the probability distribution. Again, just to understand, from a pictorial point of view or a graphical point of view, to see that yes, if you have these three investments, you could see that the risk level in A is lower than the risk level in C. So you have a lower risk here than and here there's a higher risk here. And you could just see this, and here you have almost a moderate risk. And you could just say this even without looking at the data. Why? Because you're looking at the shape of the distribution. So the shape of the distribution tells you how what is the amount of the standard deviation is in that particular distribution. So here you know that you have a lower standard deviation. Again, in this case you have 20, even just without looking at the data. But now we know it's 20. Here we know there's 190. Here we know that it's 300. So if we just look at the standard deviation only, then you'll know that this data set has a lower standard deviation and therefore lower risk. This has a higher standard deviation and therefore a higher risk. This is moderate is in between, and therefore the risk level is moderate. And the expected returns here, the good thing about these expected returns are the same, is 600. So they all have the same expected returns. So again, the larger the standard deviation, the greater, the higher the risk. The lower the standard deviation, the lower the risk. But we're going to expand on this by saying, what if the expected values were not the same? Because here they were the same, so standard deviation becomes a clear measure. It's just enough. We don't have even to go and look at the coefficient of variation, because we are looking at data that has the same expected returns and uh, different standard deviation, and therefore the one that has the lowest standard deviation becomes the one with the lower risk. But what about if the expected values were not the same? Then we have to introduce the coefficient of variation to our computations. So if we're thinking about the different degrees of risk, again, in this example, again, you could see now here is you have different standard deviation, but then the expected values are also different. So here you have 600 as the standard deviation, as 600 standard deviation here, and the expected value is 6,000. Here you have the standard deviation of 190 and the expected value of 600. So given that reasoning, which one do you think you're going to choose between the two investments? Again, the expected values are different, and there's also difference in standard deviation. For that reason, a good measure for us to do is to use the coefficient of variation to try to understand this further. But at that comparison of this standard deviation is not helpful if the expected values investment differ. And that's the true example of what we are saying. And the standard deviation of 600 with expected value of 6,000, that is for project A, indicates a less risk than the standard deviation of 190 with expected value of 600. So if you want to understand this further, what you do, you will take, of course, your 190 and divide this with 600. And you do the same thing here. You will take the 600 and divide this with your 6,000. That's in this case, you're basically saying you are taking the standard deviation divided by the expected value, and you are doing the same thing here, standard deviation divided by the expected value, and that gives you a clear cut on what is the risk by each return. And again, it just gives you an idea of which investment is more risky than others. So in this example, the risk here is you have 0.10, and of course in the other one what you end up having is a value of 0.31. So again, if you look at it, if you look at these two data, then which investment do you think has a lower risk? Of course, the truth is here you have a point 0.1 per each unit of return. Here you have 0.31 per each. The risk level is 0.31 per each unit of return. So it clearly shows you again there is a lower risk here because you're looking at 0.1, and you have a higher risk here because again you're looking at a 0.31 per unit of return. So this is per unit of return, and you're doing the same thing also on the left side. So clearly again, A here seems to have a lower risk than of course B. But again, that's how you can include the coefficient of variation in trying to determine which investment is risky and which one is lower. Again, if we just use the the coefficient of variation concept, then we know that the larger the coefficient, the greater the risk. And if I take you back to my computation here, the value here it was 0.3167 and 0.10, and therefore here the 0.3167 is higher than the 0.10, and therefore investment B has a higher risk than, of course, investment B. So again, you use this method, the coefficient of variation, especially if you find out that you have different standard deviation for projects and the returns are also different. So in that regard, the best option is to use the coefficient of variation just to understand which one has a higher risk and which one has a lower risk. Then there's also another measure that we use to measure risk, and this goes along with, especially when it comes to common stock. With the common stock, we use beta as a risk measure. So you basically compare the beta for an individual stock in relation to the market. So it's widely used with portfolios of common stock, and it measures how volatile the returns of an individual stock is relative to the stock market index, like the Standard and Poor market index. So you look at that relationship. So and therefore, an example could be if the common stock has a beta of 1, then it is said to be of equal risk with the market. And if if you have an individual stock and has a beta of 2, then we are saying it is more risky than, of course, the market. And of course, the one that is, so if it's greater than 1, so simply put it, if it is greater than 1, right, then there's a more risk. And if it is less than 1, then there is a lower risk. And if it is equal to 1, then the risk level is the same as the market. So it matches the market risk. Yeah, again, we're going to look at some examples on how we go about in trying to do all these computations and involve them again, just what we just mentioned in terms of the beta, in terms of standard deviation, in terms of coefficient of variation. And then, of course, later on, I'm going to pick up and show you how we incorporate this knowledge into a capital budget. But the takeaway from this presentation is just to show you this. You might end up having 2 projects or 3 projects, and the truth is they're going to have different risk. And because they have different risk, then in capital budgeting, what we are saying, because they have different risk, remember in our previous conversation or discussion, we were saying, oh, we're going to discount all the cash flows using a discount rate. And if you remember the example that I showed up, I was basically using 10% as the discount rate. So you can't use, in this example, you can't use 10% to discount these cash flows for this investment, and you also use 10% to discount the cash flows for this other investment. Because they have different risk, you have to use different discount rate because they're not apples to apples. The cash flows are different. Because you have 6,000 expected returns, you have 600. So in other words, the cash flows for A are different from the cash flows for B. And because of that, you cannot use the same discount rate as we saw in a previous chapter. And therefore, you're going to make some adjustment by using different discount rates. So we're going to look at this next in my second part of the presentation, the chapter, and then from there we can look at more examples on how we incorporate this into some computations. So see you in the next video.